Okay, fantastic. All righty. So your individual news item presentations are going to go like this. So they're only going to be 2 slides long. All right. So they should be pretty easy to put together and pretty easy to present. And what I want you to do is give a description of the article that you're presenting. Describe what the story is, describe what's going on there. And then on the second slide, you need to give a description about how this fits within the context of sustainable energy. Please make sure to cite your sources, okay? Either whether it's a news article or an actual peer-reviewed study itself, make sure you go back there. And actually, one thing you can do is if you are presenting a news article, a lot of the time they will be reporting something that was published in a peer-reviewed journal article. And it never hurts to go back to the original source because you might find a cool graphic you can put up or something like that, or some additional insight that you can put into your presentation. So, you can take a few minutes to do that. Best practices for presentations is that you should use a large enough font that it's readable from the back of the room. I remember learning a guideline for this, which is that your font size should be something like the age of the oldest person in the room plus 18 or something like that in points. Okay, I'm 43, so you don't have to use 61 point font. But anyway, yeah, make it big enough to read. Make graphics large. And if you can, make sure that they're not pixelated, just so that they look nice. Speak so that we can hear you. The microphone here is an excellent tool for doing that. And make eye contact or pretend to make eye contact with the audience when you're talking, because that keeps people engaged, okay? You don't just want to be looking at your slide the whole time, right? That's not how to get points across. Okay. So that's what I'm looking for. 2 slides, describe your story, cite your sources, explain how it fits within the context of sustainable energy. Question? As long as you're not like rushing through it. Yeah. That's fine. Okay, how about this? 2 slides minimum. If you want to take more slides, that's on. The one I'm going to show you, I kept it to 2 slides. If you're a multiple slides kind of person, that's fine. All right. Where to go for articles? Major news websites are always a good place to start. I actually, when I was putting together the news item I'm going to show you guys in just a minute, first thing I did, I went to the New York Times homepage and I scrolled down and boom, there was a story. It took me literally 20 seconds to find it. So, don't worry about searching too hard. So there's, major, major publications are okay. Major industry publications, the ones I've listed here are kind of specific to oil and gas, but they do have a lot of stuff about energy transition. Journal of Petroleum Technology in particular has some really good kind of decarbonization stuff in it. So I encourage you to look there. Scientific journals like Science, Nature, Scientific American, any of those are good. And you can even probably find stuff kicking around on social media. The thing with social media is that I don't want you, presenting us something you actually saw on TikTok, okay? Actually go to the source. Okay, that's fine. You can find out about it from social media, but then go to the source and actually show us what that person was talking. Okay, so that's what I mean. You have to show that your source is reputable. Okay, Mr. Beast, he's cool, but we can do a little better than that. Okay, so with that being said, let me show you an example here. So here's Daigle's news item for August 28th. So I just found this on the New York Times the other day, and it's an article. It's called "Hungry for Clean Energy, Facebook looks to a new type of geothermal." And in this story, it's talking about how a lot of the tech companies now are looking to use lower carbon sources of energy specifically to power data centers, okay? So data centers are these huge server farms that power cloud computing, artificial intelligence, a lot of the stuff that is used in today's information economy. And they use 4% of US electricity right now, but by 2030, that's forecast to jump up to 9% of electricity. Okay, so you might be thinking, well, why can't we just power these things with solar or wind? That's the obvious solution. That's zero carbon right there. The problem with that is that data centers need to be going 24 hours a day. So unless you can come up with a very clever energy storage solution, you really need something that is giving you, they call it clean, firm energy 24 hours a day. And so geothermal and nuclear right now are really the only two technologies that can offer that with low to zero carbon electricity. So let's see, the article, well, no, actually not, the article wasn't about this, but previously Meta, no, this was what the article was about. I'm confusing that with Google, sorry. So in this article, they say Meta just signed an agreement for 150 megawatts of advanced geothermal to power some of their data centers. They signed this agreement with a company called Sage Geosystems. Similarly, this was in the news earlier this year. Google is partnering with Fervo Energy for a pilot plant operating at 5 megawatts. Just for a point of reference, 150 megawatts is roughly enough to power about 44,000 homes. So this is a fairly sizable, utility scale geothermal situation. And the reason that this is happening now is because there's been, suddenly a whole bunch of advances made in drilling and completion technology for what we call enhanced geothermal systems, which we'll talk about in our geothermal unit. But this makes utility scale geothermal energy generation feasible with only a small number of wells. You don't have to have like 500 wells to generate enough heat to generate the electricity. So it's really something that's just happening now. And I think, and I hope we'll see more of this. So how does this fit within the context of sustainable energy? Well, right now, if you look at the United States as a whole, 80% of our electricity generation comes from non-renewable resources. So mainly natural gas and coal. So this is according to the DOE. If we want to hit this target of limiting average global temperature increase to 1.5 degrees Celsius relative to the 1850 to 1900 baseline by the end of the century, we need to decarbonize our electricity sources because that's still a lot of emissions being produced. And data centers, this has been in the news a lot recently also, just the growth of data centers, okay? There's a lot of them, you read about the difference in energy consumption between when you Google something and then you ask the same question to ChatGPT. It's a couple of orders of magnitude more energy to run those AI type things. And as those become more prevalent, we're going to have an ever increasing need for electricity. So we need to be able to do that in a sustainable way. And just the last bullet point here, both Sage Geosystems and Fervo Energy are based in Houston. And I think that this highlights how Texas is and will continue to be the energy capital of the world. So yeah, all right. Our expertise is invaluable. Okay, so that's an example of a news item. So on Friday, we can I'll take all comers on Friday who want to do their news items, but that's what I'm looking for. If you want a slick looking slide template, I have put this PowerPoint presentation on Canvas, so feel free to use it, or you can use whatever you want. Okay, any questions about that? Right here. So the question is, do y'all need to let me know ahead of time if you want to do the presentation? You can if you want, but it's not necessary. If you just want to show up that day and say, hey, I'm doing a news item, that's fine. I won't say no. All right. Any other questions? Fantastic. Okay. Great. Done with you. All right. Before we get going back on the lecture, I want to show you guys something that I came across earlier this morning when I was doing my regular daily procrastination, which is where I just Google stuff instead of doing actual work. It's a lot of fun, actually. But this is an article, it's actually from 2020, from Global Biogeochemical Cycles, and it's about changes to carbon isotope concentration in the atmosphere over the industrial era. So going back to mid 1700s. I think I forget how back their time series goes, but anyway, it's a little bit more of a sophisticated explanation of carbon isotope fractionation and how well constrained the fractionation in CO2 produced from combustion of fossil fuels versus other sources of CO2 is. And so I just want to pull up this figure right here. So this is showing the different kind of reservoirs of carbon that give rise to the observed fractionation that we see in the atmosphere. So as I said, so they're giving a slightly different range for fossil fuels, but the delta carbon 13 in fossil fuels, they're estimating is between -44 and -19, I can't read numbers, per mil. And again, that is because of the preference of carbon-12 in the photosynthesis reactions, because it takes slightly less energy because it's a less massive atom. Similarly in the biosphere, you've got similarly depleted isotopic signatures. The delta carbon 13 in the ocean is very close to zero, and actually that makes sense because the standard we use for delta carbon 13, remember again, is Vienna PD belemnite, which is a fossil. So this was a marine organism. And so you'd expect the delta carbon 13 of that particular rock to be zero, because that's the standard. So the ocean is still pretty close to that. The atmosphere is, in 2015, it averaged -8.4 per minute. So slightly depleted, not nearly as depleted as fossil fuels. But the atmospheric CO2, it's a mixture of combustion products, but also CO2 from other sources, including volcanoes. And volcanoes actually tend to have an enriched delta carbon 13, so it's positive. So you mix those two sources together, you get something that is less depleted than fossil fuels, but less enriched than volcanoes. And so you can back out then, knowing what the typical isotopic signature of volcanic CO2 is, you can figure out how much of the CO2 in the atmosphere came from the combustion of fossil fuels by just doing a simple mass balance. So that's how we arrive at that. The other interesting thing you'll notice here is that they compare this to values from 1850, and I didn't read about how they got that, but it's presumably from ice cores. You can see that the atmospheric CO2 has become more depleted over time since 1850. And this is an effect called the Suess effect, and it is due to increased combustion fossil fuels over that period, adding more and more depleted CO2 to the atmosphere. So that's just something else. Another reason that we know that that's fossil fuel CO2. Right here.
That be depleted or enriched? Is that like plants should be zero, right?
So, okay, so we use words like depleted and enriched, and you think enriched is good and depleted is bad, but it's really just referring to how much carbon-13 you have relative to that standard. So plants will be depleted, and the reason for that is that when they go through photosynthesis to make the chemicals that build themselves, they preferentially incorporate carbon-12. And so that just gives them less carbon-13 than this random fossil that we decided was going to be the standard for carbon isotopes. Okay, great. Any other questions about it? That's your geochemistry lesson for today. Okay, so I kind of have made this point enough here. That's because of isotopes. Also, there's no carbon-14 in fossil fuels because they're all very old. And so that's what you look for. Okay, and so now we know that a lot of the CO2 in the atmosphere is coming from the combustion of fossil fuels. so what, right? CO2 is plant food. Probably heard that before. Here's the deal. We can model the effect of atmospheric CO2 on global temperature simply through what we call radiative forcing, which is a fancy word for the greenhouse effect, right? So sunlight comes in, hits the ground, tries to get back out into space. The carbon dioxide in the atmosphere preferentially lets certain wavelengths through, and it preferentially traps other wavelengths, or it doesn't let them through, particularly infrared, which causes the atmosphere and consequently the Earth to warm up. And this is a nice chart from the IPCC interim report in 2021. The IPCC is the Intergovernmental Panel on Climate Change. And they just published this compendium of different predictions from models going back to the 1970s. So some of these were published in the 1970s. And then they're just comparing that to the actual observed temperature change since then, going up through 2020. That's what this dark line is. And you can see that there's remarkable agreement, remarkable predictive power, excuse me, just based on from what they thought CO2 concentrations were going to do back in the 1970s. And the ones in particular are these three, the Manabe, Nordhaus, and Hansen curves, which they're the ones that only consider radiative forcing from CO2. So you can explain the observed temperature anomaly since the 1970s purely through this CO2 heat trapping effect. So that's the deal. So to summarize here, what we know that atmospheric CO2 levels are higher than they've ever been in the past 800,000 years from ice cores. The recent rapid rise in atmospheric CO2 tracks fossil fuel combustion, and we know from the isotopic signature of atmospheric CO2 that what the contribution of fossil fuel combustion is, and we know that that is contributing or even causing the increase in global temperatures that we've had since going back since the mid 1800s. Okay, so that's larger point. We cannot just keep pumping carbon dioxide into the atmosphere. It is doing bad things to the climate. Now, the other thing about the current way we produce energy is that it's not just the temperature we have to worry about. Okay, there's also air pollution in general. So whenever you burn, I'm going to pick on coal for a minute. Whenever you burn coal, generally you're not burning the whole thing and just producing CO2 and water. You generally have incomplete combustion, and that produces particulate matter. And particulate matter is a really serious global health concern. Actually, I just heard on the radio this morning that the air quality in the Austin area now is out of compliance with EPA standards for a particulate matter. So even just like walking around Austin, this is something we have to worry about now. The big deal here is what we call PM 2.5, which is particles smaller than 2 microns in average diameter, because these are things that can get through your lungs and into your bloodstream and do all kinds of bad things to your organs. And this is a study, or a couple of studies from 2019, and this is too small on my screen, I can't even see it, but what we're looking at here is estimated total number of deaths due to particulate matter by world region. And you can see, particularly in East Asia and South Asia, they estimate, tens to over 100,000 deaths each year attributable to just people breathing in particulate matter over the course of their lives. Here's another paper. This study is looking specifically in India, and they are looking in different cities in India to see, as a function of the city's population, how many deaths do they have attributable to excess PM 2.5 particles. So again, you can see that it's, this is a global health problem, and it's also something that, needs to be addressed when we're thinking about the way we're getting our energy. There's also, this problem with people who live near fossil fuel infrastructure that they generally see increased cancer rates. So this was a study from 4 years ago by Williams et al., and they're looking at rates of certain types of cancer and the spatial correlation with oil refineries. So, you can see with these, with all these different types of cancers that, generally, not always, but in general, you see those increased cancer rates with greater proximity to oil refineries. So there's something of a spatial correlation there. And then this slide just looks again at the relationship between fossil fuel production, fossil fuel infrastructure, and poverty. So this is on the right here, we're looking at Philadelphia and then Minneapolis-St. Paul region in Minnesota. And you can see that in both cases, there's a couple of oil refineries that are located in or close to lower income parts of the city. And this is a pattern you see around the country and around the world. Also happens, even in California in terms of oil well permitting. So there's also the kind of energy, they call it energy affected communities aspect of this that we have to think about. And this is actually a big deal moving forward, that when we think about the solutions to these types of energy problems and creating more sustainable energy, we have to keep in mind that the solutions we come up with are still going to impact people. Okay, so like you're drilling a geothermal well, you're still going to need drill rigs, you're going to be drilling, you're going to be fracking, the whole thing. Okay, and you have to think about, how do we do that while minimizing the harm to some of these communities? So that's another aspect of that. So the upshot here of this second part here is that our continued use of fossil fuels has had and will continue to have environmental and social consequences. And so how do, what about just moving to completely renewable energy? Just say, okay, no more fossil fuels, let's just do renewable energy. Then what? And so that's going to be the next topic that we'll talk about. Okay. Questions on? Right here.
Like Texas Maverick should be.
Yeah.
Isn't it also though a lot of like towns where there's oil refineries, there's like also tend to be like food deserts and have less access to like healthy food and like good healthcare and stuff like that as well.
Yeah, absolutely. So that's a really good point, that there's all these compounding factors that result in these health outcomes. And it's difficult to untangle the causative relationships there, right? It's like, did they put a refinery there because it's a food desert, or is it a food desert because there's a refinery there, or is there something else going on? So, it can be really complicated to untangle these things. So it's part of a larger kind of public health picture that we need to be aware of.
Okay.
Yeah. Cool. All right. Okay, so let's see, unit 1.3, I should have pulled this up already, here it is. All right. And I made an updated version of this slide deck this morning because I found a cool article about lithium extraction. So if you've downloaded this already, you can go back and grab the newest version from Canvas if you want. Okay. So this is just a recap of what we just said. What if we just move to renewable energy? Does that make everything good? Do we have to not worry about anything anymore? Well, let's talk about that. It's not that simple. Okay, I guess of course it's not that simple. Otherwise, I wouldn't be bringing it. But let's talk about that. Okay, so electric vehicles have been increasing in sales in recent years. Let's see, this was a New York Times article from about a year ago, and this is looking at the fraction of vehicle sales that have been electric in the US, the European Union, and in China. And if you were to plot this and include data from 2023, China would be somewhere even higher. They are selling electric vehicles like crazy over there. So, you know, and even in the EU, it's over 20%. So a lot of new vehicle sales are electric and will continue to be so in the future. Okay. And so, you know, there's a whole kind of subgenre of memes on social media dunking on people who drive Teslas and have snarky license plates, like this one says "Forget Oil." Okay. But the reality is, it is impossible to make an electric vehicle without using any fossil fuel at all. Okay. Obviously, when they drive, they're not burning fossil fuel. Depending on where your electricity comes from, there may be CO2 emissions associated with that. But the vehicle itself also contains a lot of stuff, including plastic, which is made from oil, and coking coal, which is something that comes out as a byproduct of steel refining, which, as we'll see later on, also releases a lot of CO2. And then the steel itself, which is a large, you know, steel refining is a large emitter of carbon dioxide. So already, you know, before that vehicle has even charged its battery, it already has carbon emissions associated with it that are inescapable. Okay. Oh yeah, and then the tires. The tires are made out of rubber. Rubber used to come from trees, but now rubber is synthetic and it's made from oil. So again, you've got carbon emissions associated with this vehicle. Question? So yeah, so about recycling the batteries. Yeah, the batteries contain a lot of stuff. So I think, yeah, we'll get to that in a minute. But yeah, the batteries also are problematic for several reasons. Okay, so you know, so okay, so the question then is, you know, with all this stuff, and we'll get, you know, with the understanding that we'll talk about the batteries in a minute, are electric vehicles really that much cleaner than internal combustion engine vehicles? And let's see, this is kind of the best, most recent figure I could find. So what we're looking at here is, you know, if you buy your car in year 0, and then you keep it for a certain number of years, this is on the y-axis here. It is cumulative CO2 emissions from the operation of the vehicle, and it's in millions of grams, which is not really that useful a number until you realize that 1 million grams is 1 metric ton. So this is, we're looking at metric tons over here. Okay, so so let's see. Toyota Corolla, that is going to be our reference internal combustion vehicle. And so you can see that obviously building that car, it kind of has the same issues that the Tesla has, that it's got steel and rubber and plastic and stuff in it, and then the energy required to manufacture them. So you're starting off already having spent about 5 tons of CO2, or emitted about 5 tons of CO2. And then obviously, as you drive that Toyota Corolla and continue to burn gasoline, over 13 years of the lifetime of that car, you have emitted total about 65 metric tons of CO2. Okay, so that's our baseline, and that is just with typical gasoline composition that we have here in the US. If you go to other parts of the world, they have different gasoline compositions. So that number is going to be down, but that's going to be our baseline here. I'll add kind of as an editorial comment here that driving a car for 13 years is actually a good thing. So that's, if you can make it that long, that's pretty good. All right, now let's compare that to our Tesla. And we've got 3 different scenarios here for our Tesla. And this is based on where the electricity is coming from. Okay, so we've got the green line, that is typical US mix of natural gas, coal, and renewables. And then the blue line, that is if your electricity comes entirely from coal. And then the purple line is if your electricity comes entirely from hydroelectric. Okay, so you can see that if you're getting all your electricity from coal, you really don't come out ahead relative to driving an internal combustion engine. Yeah, question over here. Does battery efficiency play into this here? That is a good question, insofar as it affects how frequently you have to charge. Yes. So if you can get by with less charging, then even with the coal-fueled Tesla, that number would come down a little bit. If you get by with, what's that? Also the deterioration of the battery. Yeah, so that's not considered here. So as the efficiency of the battery goes down, right, you'll have to be charging more frequently. And so yeah, you'd have upward curvature in that case. Okay. If you're getting your electricity from hydroelectric, there's basically no CO2 emissions associated with that. And then typical US electricity mix, you still have net CO2 emissions, obviously, because your electricity is emitting CO2, but you're somewhere in between there, okay? So, anytime you hear the claim that, electric vehicles are, carbon neutral or carbon free or anything like that, that's really not the case, even if you're getting 100% renewable electricity. And the reason for that is simply because of the manufacture of the vehicle, okay? And the big problem is the battery, okay? Batteries are heavy. They're a little more than a quarter of the total weight of the vehicle. It gives them actually a very low center of gravity, so they're actually very safe in vehicle-to-vehicle collisions. But they're made up of a whole bunch of different stuff, including cobalt. I will keep coming back to cobalt during the semester because there's problems with cobalt. Lithium, we'll talk about lithium also. And then there's also lithium salt in the electrolyte, okay? So there's stuff in here that, number one, has to be mined. And so mining has a lot of carbon emissions associated with it. Number two, as we'll see, there's also some kind of societal impacts to these mining operations that we'll talk about briefly. And then whenever you have to recycle these batteries, some of these materials are toxic. You wouldn't want them getting into the groundwater, and they can be difficult to handle in a battery recycling plant. So there's energy and there's CO2 emissions and cost associated with that as well. All right, let's talk about critical minerals for a little bit. Critical minerals are any element or mineral that is necessary for energy production. So it doesn't just refer to renewable energy. Question back here. Yes. So the question is, can we somehow optimize use of renewable energy to help the battery last longer? That's a good question. I know that recently, I think it's Tesla rolled out a feature where it will somehow figure out what the current mix of electricity generation is and optimize your charging time for times when you've got more renewable energy on the grid. In terms of helping the actual battery efficiency, I mean, as far as the battery is concerned, electrons are electrons, right? It doesn't really care where they come from. So I don't know if there would be an effect on battery efficiency. However, I could imagine a situation where as the battery efficiency degrades, you could change the algorithm of when you charge and how rapidly you charge to try to minimize the carbon emissions associated with the electricity you're pulling. That would be fairly easy to do. So for example, here in Texas, the Electric Reliability Council of Texas, which is the entity that manages the state's electric grid, they, every 15 minutes, update what the mixture of electricity generation is. In fact, so now we're going to go down the rabbit hole since you invited me. And we're going to pull up the ERCOT dashboard. See, it's, so if we go to grid information, current system conditions, let's see. How do I get to this? Oh yeah, here it is. All right. Let's see. Generation. So it's somewhere in here. Let me find the ERCOT dashboard. There it is. There we go. Here it is. Okay, so let's see. Oh yeah, so here's the fuel mix right here. So this is as of 8 minutes ago. We were getting 25.6% of electricity from solar. Okay, that makes sense. It's a pretty sunny day out there. Not very much from wind. I guess it's not a very windy day. And then almost 50% from natural gas. Okay, so, you know, on a day like today where it's not very windy and you want to optimize when you're charging your electric vehicle, now would probably be a good time to do it if you want to minimize carbon emissions because the sun is shining. If you tried to do it at night, there's no sun, and apparently it's not very windy, and so you'd be pulling a lot of natural gas and coal electricity at night. So it's just something to consider. Tommy.
They track like that kind of like source of energy for like choices in the governmental sector, like what things to invest in, like are people using for energy, less energy for how the renewables work, or like I don't see a reason to like care about like what energy is going into your field besides like the field.
Yeah, so the question is, can this be used in any kind of policy decision type stuff? Okay, so in general, electricity produced by wind and solar is less expensive than electricity produced from combined cycle natural gas plants. And the reason for that is that natural gas plants just require a lot more maintenance and upkeep. They're more complicated, and so they have higher overhead. So purely from a price perspective, it makes more sense to try to maximize the amount of wind and solar you have on your grid. The problem with that then is that you come into these intermittency issues, which is that, you know, the sun doesn't always shine, the wind doesn't always blow. And so what do you do in those situations? Do you either rely just on natural gas for those situations, or can you somehow design the market to incentivize the creation of more energy storage? Last year, ERCOT put a few new market rules in place to incentivize batteries. And so actually right now, oh yeah, so here's the energy storage resources dashboard over here. So right now you can see that mostly the batteries are charging right now because it's sunny. But then typically like on a hot day in the summer, when you get to like the 4 to 7 p.m. time range, those batteries will start discharging. And the battery facility operators actually make money, quite a bit of money from doing that. And so, you know, that there are ways of doing that. Cool. Okay, I'm going to haul myself back out of the rabbit hole here and go back to talking about electric vehicles. Here we go. Okay, so, oh yeah, we were talking about critical minerals. Okay, so this is a non-exhaustive list of critical minerals. I think the US Department of Energy defines something like 50 of these, okay? And these are just like the most important. And so what we're looking at here is for different types of transportation or electricity generation, how much of each of these critical minerals is used. And so the x-axis here is kilograms, either per vehicle or per megawatt of electricity generated. So you can see, obviously, that the electric car contains a whole lot more critical minerals than the internal combustion engine car does. So, you know, they both contain copper. Copper is like the wiring that you use. Like every car has wires in it these days. So that's important for that. And then the other one that's used in a regular car is manganese. And actually, I'm not sure where that is in a car, but it's in there somewhere, presumably. Electric vehicles use a whole bunch of other stuff. Obviously, lithium for the battery, but there's nickel, manganese, cobalt in the battery. Graphite is used a lot, and a bunch of other stuff. The other thing you'll notice is that when we look at electricity generation, renewable energy uses more critical minerals than coal or natural gas. And that is just because of the way the devices that are used to generate the electricity are constructed. Okay, there's a lot of zinc in wind turbines, obviously copper as well. So you have to think about that. And the interesting thing about critical minerals is that as of now, the supply of critical minerals tends to be dominated by specific countries for specific minerals in a way that oil and natural gas are more evenly distributed among different countries. So let me give you an example. Let's look at cobalt. The vast majority, upwards of 80% of the world's cobalt, comes from the Democratic Republic of Congo. Contrast that with oil. The top 3 oil producers in the world, which are the US, Saudi Arabia, and Russia, it's fairly evenly distributed in terms of who's producing what. So another example, graphite and rare earths. China really dominates those markets. Lithium, Australia and Chile really dominate those. So, there's different parts of the world where, they have these very rich deposits of these critical minerals. And that's, the kind of geopolitical market for those is a lot different than it is for fossil fuels. And in fact, let's see, this is a figure from, the data are from 2019. I sadly couldn't find updated information for this, but this is one of the things, one of the provisions in the Inflation Reduction Act, which was passed 2 years ago by Congress, is to try to increase the domestic supply chain of critical minerals here in the US, basically so that we can insulate ourselves domestically from geopolitical events. I think we all remember what happened to the price of natural gas and the price of gasoline in the aftermath of the Russian invasion of Ukraine. And we have to realize that we're operating in a global market for all these commodities, and so it's good to try to insulate consumers from them. Okay. The other issue, another issue with critical minerals is that the mining itself is often socially unsustainable. And the New York Times had a good series of articles a couple of years ago about cobalt mining in the DRC. And a lot of this mining, it's in addition to kind of some of the environmental consequences of mining, is that there is a social instability that comes along with this. And so particularly in the DRC, there's a lot of, kids working in mines. There's these people, they call them kind of euphemistically artisanal miners, which are people who just like dig pits in the backyard of their house or something. And they're just working that every day in very unsafe conditions for not very much money. 35,000 children working in cobalt mines in the DRC. And so for this reason, there's a big push right now to move away from the use of cobalt in these lithium-ion batteries. And in fact, Tesla, I think most of the cars they ship now use a different type of battery, which is called an LFP, lithium iron phosphate battery, which uses iron and phosphate to take the place of what the cobalt was doing in the battery. So that's a very good thing. And actually, in this building, up on the second floor, the third floor, there's Dr. Mathuram's lab, where he's done a lot of good work looking at cobalt substitutes in lithium-ion batteries. So there's a lot of good stuff going on to try to get away from some of these more problematically mined materials. Lithium is another big one. And so lithium production right now mainly is done by pumping groundwater and letting it evaporate and then harvesting the lithium salts that precipitate. And so right now, a lot of this is done in Chile and in Australia, and they basically just pump the water out and they let it evaporate in these huge ponds. And it takes almost 500,000 gallons of water to make 1 ton of lithium. So that is a tremendous amount of water just evaporated away. And a lot of this is in water-stressed parts of the world. So that's a problem as well. I think we'll get more into lithium on Friday. Thank you all for coming. I hope you enjoy the rest of your Wednesday afternoon, and I'll see you then.
Take 4